Alright, here we are, part 4, the atom. Now the first part is just knowing the 3 subatomic particles and identifying their location, their charge, and then their size. We got protons, neutrons, electrons. Remember, protons and neutrons are inside the nucleus, and the electrons are outside the nucleus in the electron cloud. We spent a very long time looking specifically at that electron cloud and seeing how it's divided into different regions and stuff. But that's where the electrons are. Protons are positive, they both start with a P. Neutrons are neutral, both words kind of start off the same. And electrons are negative. Protons and neutrons are pretty much the same size. Remember, we came up with this, or scientists came up with this AMU, atomic mass unit, kind of this arbitrary scale or measurement. And they set protons and neutrons equal to 1, because they're pretty much equal. And then they compared electrons to it, and we realized that the electrons are so tiny that we're probably not even going to count their mass when it comes to figuring out the mass of an atom. So when we have to figure out the mass of an atom, we're just counting the stuff that really counts. The AMUs, the 1 AMUs for the protons and the neutrons. Alright, Dalton's atomic theory. We have to figure out the 4 main parts and then indicate if each part is still correct today. The first thing he said is that all matter is made up of indivisible and indestructible particles called atoms. Well, everything still is made up of atoms, but we know that they're not indivisible. Indivisible means it can't be broken down. We know that we can break it down into protons, neutrons, and electrons, and those can be even broken down into more subparticles. And then we know that they're indestructible, or we know that they are destructible. Just consider a nuclear reaction. Number 2, all atoms of the same element are identical. Well, we know about isotopes now. Dalton at that time didn't know. He said all carbon atoms are the same, all oxygen atoms are the same. Well, now we know that they could be slightly different. They could have different numbers of neutrons. He also said that atoms of different elements have different properties, and that's true. Atoms of carbon act different than atoms of oxygen. Number 3, he was dead on here. Atoms combine in whole number ratios to form compounds. We've looked at how compounds are formed, how bonds are formed, and we know that you always use whole numbers. You're never going to have a half of a hydrogen bonding with 3/4 of an oxygen atom. It's always going to be in whole number ratios. And finally, chemical reactions occur when atoms are separated from each other, joined, and rearranged. Atoms cannot be changed into atoms of another element in a chemical reaction. So Dalton didn't know about nuclear reactions. We now know that we can do more than just kind of rearrange these atoms. We can actually change them into atoms of other elements in a chemical reaction, but that's only under a special situation in nuclear reactions. Typical everyday reactions, we're not changing one element into another. We're just kind of rearranging them. Alright, number 40. Which part of the atom makes up most of the atom's volume? This is important. Most of the space is made up by that big, huge electron cloud. Remember we talked about Giant Stadium and the marble on the 50-yard line? All the seats in the whole stadium are that electron cloud. And the people sitting in them are like the electrons. They can only be sitting in one seat at a time, but there's lots and lots of empty seats, lots of space for them to be if they start moving around and change seats randomly. The second part says, which part of the atom makes up most of the atom's mass? The nucleus. Remember, protons and neutrons, they're the guys who weigh stuff. They're going to be in the nucleus. They make up most of the mass. The little tiny electrons zipping around in this empty electron cloud don't weigh much, so we're not going to even count them. So the mass is found in the nucleus. The volume, the big space, is going to be the electron cloud. Alright, Rutherford's gold foil experiment. Remember, he set up a piece of gold foil, and he had that fluorescent screen kind of wrapped around it, and he shot little alpha particles at it. And he expected those alpha particles to go right through and light up the screen back here. And instead, he noticed that a couple of them were ricocheting back and hitting the screen back here, and he wondered, why did that happen? They must have hit something solid, and they must have hit something that is also positive and were deflected or bounced back towards that fluorescent screen. So he shot positively charged alpha particles at a piece of gold foil. He expected the particles to pass through and make the fluorescent screen behind the gold foil light up, back here. Instead, every once in a while, they noticed a few flashes on the screen in front of the screen, up here. And he was confused, but they concluded that a very small percentage of the alpha particles, that's important, very small percentage of the alpha particles were colliding with very tiny dense nuclei and bouncing back. Now, if a great percentage of these alpha particles bounce back, if a ton of them hit and bounce back, hit and bounce back, hit and bounce back, if that happened a lot, then he would conclude that the nucleus wasn't so tiny. He would conclude that the nucleus is bigger because more particles are hitting it. But because just a few hit it, it must be very tiny. So he discovered the nucleus, And he concluded that it was extremely small, it was positive, and it was very densely packed. All the things inside of it were packed in tight together. Okay, number 42 says, what's the difference between isotopes of the same element, and then what subatomic particle is always the same in all isotopes of the same element? Let's tackle the first question first. What's the difference? Isotopes of the same element are identical except for the different number of neutrons. Neutrons are the key here. You have different number of neutrons if they're isotopes. And that'll change the mass of the atom, so the mass will also be different. What subatomic particle is always the same? Protons. Protons have to be the same in order to be the same element. If you have two different numbers of protons, like if you have 10 protons and 11 protons, then you don't have the same element anymore. You have two different elements. Protons identifies the element. These neutrons just kind of pack on mass here. They'll change the mass, but the proton stays the same and helps to identify the element. Number 43, how can you mathematically determine the number of neutrons in an atom if you're given the mass number? Well, we know the mass number is whatever the mass of the atom is, and the mass of the atom is made up of the protons and neutrons inside the nucleus. So if we add up protons and neutrons, we'll get the mass number. So if you know the mass number, let's say the mass number is 10, how can we find out how many neutrons there are? Well, let's work out a problem here. Mass number is 10. You need to know what element it is. Let's say the element is boron. Boron's got 5 protons. Now, we know that 5 of them are protons. The other X amount, we don't know how many yet, the other X is going to add up to equal 10. So 5 plus, and then you can do the math, 5, would be how many neutrons we have. Protons and neutrons add up to be the grand total.